Okay, so today we are very happy to have Micheal here for the BES Tea seminar series. He did his studies in the University of Uganda, then a Master in Science at the International Center for Theoretical Physics, also the one in Africa, but it's related to the one in Trieste, for those who knows. And now he's doing his PhD in Houston with Professor Ratti. And he's mainly working on the equation of state and basically this alternative expansion to go further and further at finite density. And this for the study of the critical point and all the wonderful things that we can find at finite densities. So please go ahead, Micheal.
Thank you, Gregor, and the organizers for the invitation. So today I'm going to talk about the finite density QCD equation of state that we developed from the lattice-based T prime expansion scheme, and we introduced the critical point into this equation of state. So we'll call it Ising-TExS, basically Ising T prime expansion scheme. So this work that I'm going to present today is based on the paper that we put on arXiv last month. And let me also thank my collaborators and the funding for supporting us in this work. So to begin, just 1 second. Okay, so phases of stronger interacting matter are captured by the QCD phase diagram in its common presentation, which is temperature and chemical potential. So this phase diagram is not yet fully known, both experimentally and theoretically. But what we know is that the transition from hadron gas to quark-gluon plasma is a smooth crossover. Many QCD effective models predict that this crossover will evolve into a line of first-order phase transition at finite chemical potential with a critical point. The location of the critical point is not yet found. So what is always done is that the lattice QCD in this regime is challenged by the Fermi sign problem. So attempts are used to do direct simulation at finite chemical potential, like reweighting of the partition function. But this one is still limited to small volume. So it happens that extrapolation schemes that utilize lattice results as low chemical potential are still needed to find the equation of state at finite chemical potential. So from experiment, what is always done is to search the critical point, which is at the core of the beam energy scan experiment. So finite density physics is achieved by lowering the center of mass energy. However, from the theoretical side, hydrodynamic simulation are needed to describe the matter that is created from these experiments. Basically, describes the evolution of the fireball in heavy ion collisions. These hydrodynamic simulations require an equation of state as the input. So from our group, we developed this equation of state. The most important thing that we try to do is that the equation of state, it is important that the equation of state that you provide encompasses all the theoretical knowledge that we know, like the critical point, and also it is important that it has adjustable parameters, like the equation of state that I'm going to show, such that someone can easily compare with the experiment. Let me start by showing the equation of state that has been available for a long time, which is the one developed from the tile expansion. So the pressure is defined as the sum with expansion parameter mu b over t, and the coefficients, the chi's, are computed on the lattice. So these chi's are the derivative of the pressure with respect to chemical potential at zero chemical potential. In this talk, I'll concentrate more to the baryon density, which is the derivative of the pressure with respect to chemical potential. So in principle, to evaluate the baryon density, we need all the coefficients from 0 to infinity. However, we are limited to the coefficients. So these are the coefficients available. So here we have chi2, we have chi4, and chi. Sorry about that. So we have chi2, chi4, and chi6. So the equation of state from tide expansion scheme works well. However, it has limitations. One of them, as you can see, these coefficients, when you compute higher order coefficients, the error bars become larger. So it becomes complicated to extract the signal from these, from the higher order coefficients. Also, it was observed that the higher order coefficients are wiggly. So the more derivatives you compute, you have more wiggles. So these wiggles also appear in the thermodynamic observables. So as you can see here, so this is the series from the leading order up to next the leading order. So you can see for low values of mu b over t, we have it is well behaved, but if you keep increasing mu b over t at 3, you have these wiggles, they appear in the thermodynamics that you are computing. So this
Micheal, can I
limits
ask you a
the,
question?
yeah, you can ask a question.
Thank you. So, does this wiggle are just because of statistics, or is it just here, like lattice QCD is not able to be reliable at this mu b over t?
Yeah, so the error bars are due to the statistics, but these wiggles are due to the behavior of these guys. Whenever you take derivatives, so the first one has a bump, then when you take another one, you get more bumps. So if you compute the higher orders, you still have more wiggles. So it is the way these guys are behaving.
Okay. So, and these wiggles are a problem. They are the problem.
Yeah. Yeah.
Okay,
So
I see.
these wiggles up to this order, so they are a problem. Up to mu b over t equals to 3 or 2.5 to 3. So what is always done is to do a resummation, and you take fewer terms, as I'm going to show.
Okay, I see. So okay, I see. Thank you.
So this limits the study. So as you can see, tide expansion is limited to mu b over t less or equal to 3, despite the computational power. Also, it was studied that including one more term into the expansion doesn't remove these unphysical wiggles, because as I say that the higher order terms are more wiggly than the lower order terms. So what was done recently was the best collaboration used the equation of state from tide expansion to introduce the critical point in order to study its effects on the thermodynamics. So the way it was done was to separate the baryon density into two terms, the one that has the critical point from 3D Ising model. I'll explain more how the critical point from 3D Ising model is introduced into the QCD. So they separated the Ising and the non-Ising term such that the coefficients, the one that has the critical point Ising and the non-Ising, reproduce the lattice at mu b equals 0. So here I show you the coefficients from the best equation of state. So the blue is the Ising, the red is the non-Ising, and the black is the lattice. And this was done up to chi4. So using this equation of state, the baryon density was computed. As you can see, this is the baryon density in temperature and chemical potential. So for mu b greater than 450, there are these unphysical wiggles, and these unphysical wiggles are due to the truncation in the tide expansion. So this limits the study of the critical point or critical phenomena if the critical point exists. So here we cannot go up to, if the critical point is higher than 450, then we cannot find it. So we can only cover a range up to 400 lattice plus HRG. Okay, so what was done was that the Wuppertal-Budapest collaboration developed the T prime expansion scheme. That the way it was developed was to observe that this quantity, the scaled baryon density T chi1 over mu B looks similar at different scaled temperature mu B over T. Basically, by shifting these lines of constant imaginary chemical potential, they fall on top of each other at chi2. And this looks like chi2. So this motivates the identity that T chi1 over mu B equals to chi2, but at a different temperature given by this shifting temperature at a different temperature T prime. So this identity is mathematically consistent. As you can see, chi1 is the baryon density at mu B equals 0. Chi1, the baryon density is 0, so you have 0 over 0, which requires you to take the derivative, and then you get chi2. So I remind you that these chi's are the derivatives of the pressure with respect to chemical potential, and these are the coefficients that appear in the tide expansion. So T prime, it was later done systematically, and it is easy to see that it is an expansion when fitted to a function. So it's an expansion in mu B over T, and these kappas are the coefficients for the T prime expansion scheme. So what do we achieve from this expansion scheme? We achieve a mu B dependent temperature, which wasn't the same case in the tide expansion, because in tide expansion, you expand at constant temperature. And also this T prime expansion scheme is trusted up to mu B over T equals to 3.5. So it is easier to see that the T prime expansion scheme is basically a resummation of the tide expansion, which means that we can find the relationship between the theta and the T prime expansion scheme. So these kappas are related to the chi's. Kappa 2 is related to chi4, kappa 4 is related to chi6 through these relations here. And here I show the plot of the kappas. So the blue is kappa 2, the red is kappa 4. Kappa 2 is fairly constant in this region where I expect the critical point. And there is a separation between kappa 2 and kappa 4. As you can see, kappa 4 is consistent with 0, which hints faster convergence, but also it is important to test what happens to higher order kappas. There is also a good agreement with HRG model, which is the low temperature description of the QCD phase diagram. So
can I ask another question?
Yeah, you can ask a question.
So so the chi's here are the chi calculated on the lattice, so they contains the wiggle basically. So
Yeah,
this K2BB, K4BB, they just kind of compensate in some way the wiggles and they are more precise, or can I understand this like that?
yeah. So basically, what is done here is that these chi's have the wiggles, but it happens that you can match. So by matching kappa 2, you are matching chi 4. So it means that you need fewer terms to have the same.
Okay.
Yeah, to have a better convergence, which wasn't happening in the tide expansion.
Okay, so the intuition
But it
is
is also
like
true what Gregoire says,
yes?
that while the chi's have the wiggles, somehow the kappas are much more smooth as a function of the temperature. And it was to be expected because in first approximation, kappa 2 was even constant, right? So shifting by a constant did a relatively good job already.
Yeah.
So we expected, as it's seen in this figure. So it was to be expected that the kappas will be less structured as a function of the temperature compared to the chi's.
Okay. I see.
Can I ask here, but this comes from temperature derivative, right? The wiggles that cancel. So essentially temperature derivative of chi2 is temperature dependence of chi4.
Yes.
Right? Yeah. By some, I don't know if it's accident or not, but it seems to play out this way in the temperature range.
I think it's actually somehow motivated that two derivatives with respect to mu we
Okay.
have
So it's
are
chiral
equivalent to
scaling.
one derivative with respect to t. So
Mhm.
definitely, like where chi2 has a inflection point, chi4 as a peak, but that's also where the derivative of chi2 has a peak. So it's known feature that the structure of the two derivatives down with respect to mu b is the structure of one derivative down with respect to t. So yes, you are right. So that's
Mhm.
in a way
Mhm.
natural cancellation because of that.
In the chiral transition region, basically, right? Where we have the scaling variable which connects t and mu square. Okay.
Yeah.
And if I may, another question here. So if as far as I remember, the kappas here are actually not obtained from chi's, right? But by fits to imaginary mu data directly.
True.
Yeah, that's correct.
And so if we would have chi's with infinite precision, do they have to agree within errors or not necessarily? Like maybe by fitting some finite range in imaginary mu, they may lose the precise meaning of Taylor coefficients, right? I'm just wondering if there is independent estimation using chi's of the kappas, which can be compared to these results here.
Yeah, I think we show it in the paper. So definitely the identity is exact, but what you say about fitting a finite range in mu, in imaginary view, it's also certainly true. So it's
right.
If you knew both with infinite precision, then they would be the same.
Yeah. Well, you would have to do the fit in very small region around mu equals 0, right? These things to be equivalent, right?
Yes.
At finite mu, high order coefficients, a truncated fit is not the same as derivative, right? At
That's
that point.
true. That's
Okay.
true.
Okay.
Okay, thank you for the discussion. So continue. So this T prime expansion scheme allows us to push the results from Taylor that were limited to 450 MeV to 700. So in that case, if the critical point is there, then we'll be able to cover it. So what we did before, we know that the lattice data are given at discrete points. So we developed a parameterization to have a smooth description of the phase diagram in temperature from 25 MeV to 700. So we chose a parameterization such that we reproduce the proton mass. So MP is the proton mass in units of 200 MeV. And also we reproduce the Stefan Boltzmann's limit at high temperature. So we get a fit, and also we get a fit for chi2, and also we get the fit for kappa 2, such that we reproduce the Stefan Boltzmann's limit of kappa 2, which is encoded in this parameter A, and also we reproduce the HRG result at low temperature. So what we have now, we have an equation of state that can reach high values of chemical potential, but it's basically the crossover description. So we don't expect a critical point. So what we do, we introduce the critical point by means of 3D Ising model. So we use a strategy, we use the scaling behavior of 3D Ising model. Then we developed a map from 3D Ising model to QCD. And then from there, we merge the 3D Ising model onto the lattice. And from there, we can estimate the critical contribution from the parameters that we have from the map. So we know that if the critical point of QCD is to exist, then it should be in a 3D Ising model inverse IT class. There is a conjecture that describes that. So close to the critical point, we can always define the parameterization of the magnetization magnetic field. So this was already done in the previous work. So M is the magnetization, H is the external magnetic field, Ri is the reduced temperature, defined as this. and alpha, beta, delta. These are the critical exponents of the 3D Ising model. So G is the Gibbs free energy defined in the scaling parameters R and theta, defined by this expression. So this scaling gives us the non-universal map or non-invertible map from R theta to RH. So then we develop a map from 3D Ising model. So in the 3D Ising model, we have the critical point sits at R equals 0 and H equals 0. This side we have a crossover, and this side we have a line of first order phase transition. So we map onto the T prime expansion coordinates. So we choose the map such that H equals 0. So we first map the crossover to T prime when H equals 0, so T prime equals to T naught. And also when H equals 0 and R equals 0, so we have mu B equals to mu BC, which is where the critical point sits. So as you can see, this map has three parameters that are indicated in red. We have W prime, alpha 1, 2, which is the angle between the axes R and H. And also we have W prime and rho. These are the scaling parameters of the 3D Ising model. These are the scaling parameters of the mapping. So then by replacing back the T prime, we map on to the QCD, and I will show you how we relate it to the previous linear map that was developed by the BEST collaboration. So T prime T, this is the derivative of T prime with respect to T at constant mu, and this is done at the critical point. So T naught is the transition temperature at mu B equals 0, and these are the three parameters I talked about. If we map on to the QCD, the critical point sits at TC and mu BC, and this is the line of first order phase transition, and this side we have a crossover. So the mapping from QCD, the mapping from Ising to QCD is not universal. So in our case, we find the relationship between the mapping that we use, which I call the Texas, and with the BEST mapping, which was the linear mapping. So the relationship is given by these equations here. Basically, the way we do it, we linearize the quadratic mapping that we have around the critical point, and then we can match the terms, and then we find that this is the relationship that gives us the connection between the two mapping. Also, another important relation to see is the strength of discontinuity. So the strength of discontinuity is governed by the leading singular behavior in the specific heat capacity at constant pressure, given by this expression. So it happens that GHH, this is the order parameter, it is independent of the mapping choice. So which means that the term in the bracket is universal. So in our case, we see that W sine alpha 1, 2, this is the term that controls the strength of the discontinuity or of the jump. So basically increasing W requires to reduce sine alpha 1, 2, such that we can keep the same jump in the equation of state. So another important relation is the transition line. So from the mapping, the way we define the transition line, we define such that T prime equals to T naught, defines the transition line. T naught is the crossover temperature at mu B equals 0, given by 158 MeV. So the choice of the transition line that comes naturally from our mapping reduces some of the parameters. As we see here, we have 6 parameters that we have from the BEST collaboration. So by choosing the critical chemical potential, you fix the critical temperature, and also you fix the slope of the transition line. So this reduces from 6 parameters to 4. So the slope is given by this equation. So having TC and UBC, you can find alpha 1, 2. So these are some of the examples. So I chose 2 examples. One is when the critical chemical potential is 350, such that we compare with the best equation of state. And also I choose 500 MeV to show that we can go higher than the best equation of state. So if mu-BC is 500, then TC is 117, and also the slope is 11 degrees.
Micheal, can I ask some question before you move on? Can you go back 1 or 2 slides before? Yes, another one. Yes. So here, like the only thing that, no, it's fine. The only thing that makes the H and R directions to be like a bit bent is because you change from T prime expansion coordinate, which is 1 plus mu B over T times the squared or something. So then what we see like this from linear to this is really the square of, I mean, it's because you change from T to T prime, right?
Yeah. So this is one way.
Yes.
Yeah. So you have a square here, so it bends down.
Okay. I wanted to make sure. Okay.
Yeah, also there are 2 things. So the mapping, we choose it wisely. So we put a negative such that we invert the crossover, and then the crossover turns, and the line of first order phase transition goes where we expect it to be. So, and the curvature comes from this.
Okay. And can you comment on the fact?
This is the plot. Yeah, this is the plot in mu B squared and T prime. So this is mu B and this is T.
Okay, I see.
So all the all the axes are going to curve.
Okay. And can you comment on the fact that say H and T are opposite direction? Is it like, I know maybe it's minus W or something, but when I worked on that, I remember that I think we used H and T on the same direction, so to say.
Yeah. So from the previous best equation of state, so H faces upwards. So so here it is the same. It doesn't matter what you choose, but what you should know is that your alpha 1, 2 is going to be 90 plus your alpha 1, 2. So it's a convention. So
okay,
we chose it, because it was more natural.
Okay, thank you.
Yeah. Okay, so I was talking about this. So if we now introduce the mapping that we have talked about into the Ising pressure, this is how it looks like. So Ising pressure, or the critical pressure, is the negative of the Gibbs free energy. So we see that here we have the critical point sits at R equals 0 and H equals 0, and this is the line of first order phase transition. Here we have a crossover, and in the T prime coordinates, this is how it looks. So basically we have a minus that is in the mapping, so it inverts the line of first order phase transition. And then if we map on to the QCD, so you can see that we have 2 critical points. And this is important because the 2 critical points come naturally because they are inbuilt from the mapping, because we chose a quadratic mapping in mu B. And it is important to have this because QCD is symmetric under exchange of baryons and antibaryons. So, and these plots were done for this choice of parameters. Okay, so
and
from the Ising,
sorry, excuse me. How do you choose like the W, the rho, like the size of the critical region and stuff in this calculation? Is it just some test or from, I don't know?
Yeah, so in this, I chose them randomly. So, but I'm going to show you that we have constraint on these parameters. So here I chose W to be 10 and rho to be 0.5.
Okay, so it's arbitrary, like it's choosable in the model.
Like so from the mapping we can choose everything, but I'll show you that we can't choose everything. in the end.
Okay, thank you.
Okay, so from this Ising pressure, we can compute the baryon density, which is the derivative of the critical pressure with respect to chemical potential. So we see that we have a discontinuity, which represents a line of first order phase transition, and this side have a smooth crossover. This is baryon density in temperature and chemical potential for the choice of these parameters. So the critical point is placed at 350 MeV, and the critical temperature is 140 MeV. So now we know how to introduce the critical point into, we know how to map any physical quantity from 3D Ising model onto the QCD. So we have also the T prime equation of state that can be pushed to higher chemical potential. So what I'm going to show in this part is to merge the 3D Ising model with the T prime expansion scheme. So from the 3D Ising, from the T prime expansion scheme, we have a definition that the baryon density, which is chi1, is mu b over t chi2, but at the price of evaluating it at t prime. So we saw that t prime is an expansion in mu b over t with coefficients kappa. So what we do, we keep the low order terms to be the one from the lattice and the higher order terms to be the one that contributes to the critical point, such that t prime minus theta, if we compute all the terms, then we can always reproduce the lattice. So the way we do this is that, so from the T prime expansion scheme, the finite density physics is encoded in, as long as chi1 over mu b times t is smooth, then the finite density physics can be encoded in this T prime. So we can separate the baryon density into the term that has the critical and the non-critical. So that requires us to separate T prime into the term that has the critical and the non-critical. And from there, we can recognize that the T prime critical is proportional to the baryon density critical through this relation here. And then we can find the tide expansion up to the second order. So in our expansion, what I didn't tell you is that we saw that kappa 4 is almost consistent with zeros, so we stop at kappa 2, which match chi 4, which was the same order as for the best equation of state. So here it requires us to compute the tide expansion up to order 2, such that we can match the same order, such that the Ising can also contribute to the higher orders. So here I show you the result that we get. So after computing everything, we put T prime into this equation, and then we have the baryon density. So the baryon density will have the discontinuity through T prime. And this is the equation I'm showing you. So this is the plot of baryon density as a function of temperature, and these are lines of constant mu b over T. So the solid lines, this is our equation of state with the critical point. This is the jump, and the band, this is the lattice data up to mu b over T. So here, for the choice of these parameters, our equation of state is within the error bars of the lattice. So it is good to see that you have the error bars of the lattice, and also you have the equation of state that passes in the error bars. And also, if it is interesting, someone can use it to constrain the equation of state by making it that it should be within the error bars. And this is the line of first order phase transition. So another constraint that we talk about is that there is work that was done by Misha and Manisha. So it was done using the BES mapping, which is the linear one from 3D Ising to the QCD. So it was observed that there is a universal behavior of these mapping parameters. So there is a dependence on the physical quark masses. And it suggests that alpha 1, 2, which is the angle between r equals to 0, which is the x-axis, h-axis, and also the h equals 0, which is the r-axis. So it should vanish as the quark mass to power 2/5. And this suggests that alpha 1, 2 has to be equal to alpha 1. So we put this condition into our equation of state. So if we choose alpha 1, 2 equals to alpha 1, so here I show you the baryon density with the critical point placed higher at 500 MeV, and TC is 117 MeV. So here we have the baryon density as a function of temperature, and these are lines of constant chemical potential. So the green is the 500 MeV, and that's where our critical point is. It is expected to be continuous, and at high MeV, we expect a discontinuity. Also here, I show you the baryon number susceptibilities, which gives us the information about how the baryon density reacts when you increase the chemical potential. The divergence at the critical point, which is the green 500. So it reacts to the divergence at the critical point, as you can see here. Also, we compute. So also it is important to see how the critical points look. So we zoom in from the baryon density. This is the baryon density in temperature and chemical potential. As you can see, it goes to 700, and it has a smooth behavior. If you zoom in around the critical point, so the red dot is the critical point. This side we have the line of first order phase transition, and this side we have a smooth crossover. Also, we zoomed in into Chi2, which is the baryon number susceptibility. So it is important to see how Chi2 diverges around the critical point, and this is how it diverges. So someone can compute the scaling parameters on how it diverges. So this was done for the choice of these parameters, which are the same. Also, we compute other thermodynamic observables like pressure, which is the integral of the baryon density, entropy, which is the derivative of the pressure respect to temperature at constant chemical potential, energy density given by this equation, and also we compute the speed of sound, which is the derivative of pressure with respect to energy at constant entropy divided by baryon density. So here I show you the 2D plots of pressure as a function of temperature, and these are lines of constant chemical potential. The critical point is placed at 500, which is the green line. So in the pressure, we expect a sharp point, a kink. And here I show you the energy density. So we expect a discontinuity in the energy density. Also, these are lines of constant chemical potential. The green is where the critical point is. So here I show the 3D plots of pressure. So pressure as a function of temperature and chemical potential. So the critical point is at 500 MeV, and we expect a kink. So if you zoom in, you have like a sharp line, which is the line of first order phase transition. So we have entropy. The critical point is at the same point, 500, and we have a line of first order phase transition. And in the energy density, it behaves the way we expect. So we have a line of first order phase transition. And for the speed of sound, we expect the speed of sound to go to 0 at a critical point. As you can see, it has a dip that goes down. Okay, so the last part of this talk is the constraints of the equation of state. So we have seen from the mapping, we have these parameters that I showed in red. These are the parameters that come from the mapping, but it happens that we have some theoretical knowledge about what we should expect. So from lattice QCD, it disfavors the critical point to be less than 350. So which means that someone from our equation of state, someone can choose the critical point between 300 up to 700 MeV. Also, we saw that the choice of the critical chemical potential fixes the critical temperature and also fixes the slope of the transition line. So also, if you want the equation of state to reproduce the physical quark masses, then alpha 1, 2 is not free. It should be equal to alpha 1 like this. So we remain with the scaling parameters W and rho, which can be fixed by requesting that the equation of state has to be stable and also it has to be causal. So for stability, we request that the specific heat capacity at constant volume should be positive, and also the susceptibility should be positive, and the speed of sound should be between 0 and 1. So these conditions guarantee that the pressure is positive, baryon density is positive, entropy is positive, and all the thermodynamic observables that are supposed to be positive are positive. So this restricts the choice of W and rho. I think this is the question, Gregor, you were asking. So it restricts the choice of W and rho. So the blue are the points that are acceptable, the blue dots, and the red squares, these are the points that are unacceptable. If the critical point is chosen to be at 500 and imposing the condition that the equation of state should reproduce the physical quark masses. Okay, so what we did next was to compare the scan of the parameter space W and rho from our equation of state to the one that was proposed by the best equation of state. So we put the critical point at the point where the best equation of state can reach, which is 350 MeV. And we do it for alpha 1, 2 equals to 90, which is the condition that was chosen by the best equation of state. So we see that our mapping favors more acceptable points, and these ones are indicated by the triangles. So the triangles are the points that were unacceptable in the best equation of state, and they're acceptable in this new equation of state. And here, if we impose the condition where alpha 1, 2 equals to alpha 1, which reproduces the physical quark masses, we see that we have more points that are acceptable compared to what was presented in the best equation of state, which shows that the quadratic mapping, of course, if you go to higher chemical potential, it will be better than the linear mapping. Okay, so I summarize the talk. So what we do here, we don't predict the location of the critical point. However, what we do, we have showed that we provide an improvement of the best equation of state, which was limited for 450 MeV. So we have an equation of state with 3D Ising model critical point that can go up to 700 MeV, and it is matched with lattice at low chemical potential. Also, our equation of state incorporates the charge conjugation symmetry that is inbuilt in the mapping, as we saw that we have the symmetry between baryon and antibaryon exchange. Also, our equation of state, which we call Ising-TExS, has the ability to be constrained to reproduce the physical quark masses by imposing that alpha 1, 2, which is the angle between the h-axis and r-axis, to be equal to alpha 1. So we have an equation of state that can be used for hydrodynamic simulation with adjustable parameters. So you have more parameters to adjust with constraint of what those parameters should be. And from there, the user can constrain and compare with the experiment, which are the B-Manager scan experiment. So I thank my collaborators for this work, and our work is available on archives, so you can always check it out. Thank you for listening to me. So before I conclude, I want to talk about the code. So our code is available. It is in C++, so it is available on this link. And also it will be available in the Muses collaboration. So we are planning to do the alpha release. So stay tuned in around May. So you can check on the website to get updates about the recent developments in this work. Thank you very much for listening to me.
Thank you, Micheal. Is there any question from the audience? Okay, I see no questions. So me, I have some. So let's go. Yes. So at some point you were talking about that you trust this expansion more than the previous one, the Taylor one, and you just mentioned that that you can have like you have triangles in the row W plots that you have, which I understand. But is there like something more, so to say, mathematically, like the radius of convergence of this expansion or something related to that, to like really quantify if it's better or not going further in the phase diagram, or is it just because rho and W can go further?
Yeah, that's a good question. So currently, that's the work that we are working on. So we are trying to test like what is how strong this T prime expansion scheme is. So how far can it go? So it is something that is ongoing now. So we are testing it in other models like HRG model.
Okay.
So yeah,
but basically it will be a numerical test, or there is no like something analytical like beforehand that you can just state directly. It's just that you have to test and see. Okay.
Yeah, it is hard to compute the radius of convergence because it's not like a normal expansion, like as you see in tight expansion. So you have the T prime that enters into chi. So we are still figuring out. So also we don't have enough terms to compute the radius of convergence. Because it is still Taylor, so it has limitations as in Taylor.
Okay.
Yeah, it is still under study.
Okay, thank you. So can you go on slide 18? Please, thank you. Yeah, so here, like you have so the bands are from lattice calculation, if I understand properly, and the equation of state that you produce is within the bands. But how does that depends on W and rho? And can you constrain that directly with this with the lattice calculation, or?
Yes, so these parameters, they depend on W and rho. You could choose W and rho where the equation of state is outside the band. Yeah, it doesn't mean that it may not be valid or invalid. So this is if someone wants the equation of state to be within the lattice or close to the lattice, but with a critical point. So the W and rho are not constrained by this.
Okay.
So we haven't imposed constraint on this because even it's not a guarantee that it should be within the error bars of the lattice, because this is up to kappa 4, but if you add more terms, then so the lattice is computed up to kappa 4, but if you add more terms, then the lattice could be different.
So yeah, from this you cannot learn much more than the stability and causality constraint that you had on the rho and W at the end, like the last plot.
No.
Okay, I see. So on slides where you show the CS squared on 3D, I always have this question, so I take this opportunity to ask it. So like this 3D plot you have, it seems like the CS squared has kind of two dips, not only one. So it reaches 0 once, yes, but it has kind of two dips. So I was just wondering why is that? And
yeah, that's a good question. So around the critical point, like we have a lot of numerics. So in principle, if we did everything analytically, so it should have one dip, but we do numerical derivatives because the expression for CV has higher order derivatives up to second order. So it is challenging to compute derivatives here. That's why it has those
Yes,
two
okay.
dips. Numeric,
I see. Yeah, I mean, numerics prefers when everything is super smooth, I guess. Okay.
Yeah.
Yes, and I have one last question, or maybe two, I don't know. So you said that so this expansion goes up to 700 MeV or 800,
700, yeah.
700. So at some point you mentioned that maybe you can put the critical point up until 700 MeV, and I just wonder if there was like some boundary problem issues or things like that numerically, which can happen if you put the critical point too close to the limit. I mean, to the range. Yes.
Yeah, so that's true because we do numerical derivatives. So what I do in the equation of states, I compute up to 700. So we have an equation of states, so you can give it the limit. So you can go up to like 701 and then or 702. And the numerical derivatives can allow you to put it at 700. But it's true, we have the boundary problem. So you cannot put it exactly at 700, but unless you push it at 701, because if you go higher, it is basically the same thing. It's just constant. So it's just
Okay.
constant.
It's just like
so you can still
moving
put it at 700. Yeah.
Okay. 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 So yeah, thank you. I think it's all the questions I have. So is there
Okay.
any more question in
Could
the
I ask
audience?
some?
Go ahead, Olivia.
Yeah. Yeah, I was wondering, how does the mixed phase region looks like in this construction? In particular, if you consider quantities like pressure as function of density, because that's what you need in hydro, I think, right? Not as function of mu b explicitly, but as function of density. Like you,
Yeah, I haven't.
typically you would have, you could imagine some Maxwell loops there, right? Generically speaking, and this is something which maybe from mu b, as when you look at function of mu b, is not very explicit.
Yeah, it's important. I can try to calculate the pressure as a function of density and I see what happens. So that's why it is important for the theorists to talk to people in hydro such that we can know what is really needed for us to develop. Yeah, I haven't looked through what happens as a function of density, but it's interesting to do.
Yeah, well, if I understand this correctly, right, since you have everything as function of mu b, you would have a jump, right? So you would just have, right? So you have a jump in density when you, so you have to somehow, if you now look at equation of state as function of density somewhere inside the jump, then you have some freedom, right? So you could, you could connect it by straight line, or you could do some Maxwell. So there is
spinodal region.
If I understand this, yeah, spinodal region. If I understand this right, this is unconstrained at the moment by this construction, or is it?
I think it is unconstrained. I'm not sure about that.
Okay.
Yeah, I have to check because we didn't impose any condition on the spinoidal region unless they happen in the Ising model, and because I think if we have them here, then they should also happen in the Ising model.
Yes, yeah, that's of course a good question, right? Also, yeah, I think there is some dependence like on critical exponent, like in the mean field limit, it's you have this Maxwell loops, but when you have 3D Ising exponent, things get a bit more murky.
Yeah. Yeah, in the mean field limit, we found the branches in the Ising model, and then in the 3D version, we couldn't find them. They are somewhere in the complex plane.
And maybe a completely different question. What is Zenodo exactly? You had
Oh,
a slide.
yeah, Zenodo actually is an interesting thing that I found by discussing with Andrew and Johannes. So Zenodo is some link where you can publish your code.
Mm-hmm.
Can always update your code anytime that you want. So you can link it to the GitHub. So it gives you the DOI. So you can publish your code and get the DOI. So there are many codes that are always published on Zenodo all the time.
Okay, so it's the DOI, right? Is the
Yeah, it's like the archive, but for code. So all these are codes that are being published. If you check, they are published today, 19th March. So today, so it gives you the DOI, and you can link your paper to Zenodo, so someone can see your code and your paper.
And so that's the difference to just updating it on GitHub is that you get digital object identifier.
Yeah, and one other good aspect of that in terms of let's say release policy and everything is that at least you have like you have a static version of the code that you post online as like basically the version of the code as it is when you publish the paper. So people can use the code and reproduce the results from the paper without having to dig into your different updates if you just provide a Git link, for instance.
Yeah, okay.
So that's also the reason why we use that.
Yeah. Well, I mean, on GitHub, you can also create releases. The only difference,
yeah, sure,
that you don't have DOI, right? Or is there any?
Yeah, exactly. That's the thing. Here you have a DOI, so that's also the strong point of Zenodo.
And so if you edit
and you
here,
can
right,
edit.
you get a new DOI, or what happens?
No, like if you update the
Yeah.
same code, the DOI stays the same, but someone who checks it gets the new updated code. So you can always come.
Okay.
No, and it will be written on the website that the version has been updated, and I think they indicate the date at which it was done. So you still have track of the history of the uploads.
Okay, thank you.
Yeah, it's a good thing to check out.
Okay, any more questions? So if not, yes, let's thank Micheal again for his very nice talk, and see you in 2 weeks for the next BES Tea seminar from Nikki Mullins and the stochastic hydro and constraints. So thank you very much to be here. See you.
Thank you.
Bye.
Thanks,
Thank
everyone.
you.
Thank you, everyone. Bye-bye.
Bye-bye.